Thank you for joining today's webinar on designing low-power energy applications for NB-IoT and LTE-M networks. Today we have Sierra Wireless and Altair with us to talk about these two LPWA technologies and the power-saving techniques required on both the network and device side to ensure your deployments last for years in the field. First up today will be Nicholas Damore. Nicholas is Director of Technology Partnership Development at Sierra Wireless, responsible for standardization activities and for innovation projects with industry partners. Then we have Dima Feldman, who's the Director of Product Management at Altair Semiconductor. Dima is responsible for leading the company's product management, product marketing, and architecture solutions. And then Remy Marcotocchino will wrap things up. Remy is the Director of Market Strategy at Sierra Wireless with worldwide responsibilities in the industrial and security markets. Over to you, Nicholas.
Hello everyone. So my name is Nicholas Damore, and I work for Sierra Wireless. And together with my partner and colleagues Dina and Remy, we'll walk you through today a number of considerations to keep in mind when designing low-power applications. So we'll start with some theoretical aspects. So I will be speaking about that first. So also about deploying solutions in LTE-M and NB-IoT networks. Then Dima will deep dive a little bit more into power consumption considerations before Remy takes us through some explanations about how to optimize data collection strategies for LPWA applications. So to give you a first overview of LPWA technologies, one thing we should keep in mind here on this slide that we can see that you have mainly two big branches of LPWA technology. So on the one hand, on the right-hand side, you have a number of technologies, LPWA technologies, that have been developed in proprietary ways. They came faster on the market, and they've been around for, I would say, probably 4 to 5 years for some of them already. These ones are the most famous ones. There are a number of them, but the most famous ones are certainly LoRa, so LoRaWAN. You also have Sigfox, which is quite famous, and Ingenu, so owner of the RPMA technology. So these technologies recognized earlier, and the companies behind those technologies recognized earlier, very early on, that there is a need to have IoT solutions that, while still ensuring wide and deep coverage, you need to reduce power consumption compared to your regular legacy cellular IoT solutions. On the left-hand side, you have a stream of other technologies, LPWA technologies as well, so low power wide area, that have gone through the process of standardization. They have gone through the forum called 3GPP, where many companies of the cellular ecosystem have come together to agree on standards. And it came out 3 standards, actually. One that's called LTE-M, so M for machine, which is also known as EMTC for Enhanced Machine Type Communications, or sometimes CAT-M or CAT-M1, referring to a category of device. This is the closest one. This is the 4G technology and the most natural evolution of 4G networks for LPWA networks. You also have narrowband IoT, which is a second standards-based LPWA technology. It's also a 4G technology largely based on LTE as well, with some small additional characteristics. As the name says, it's using less spectrum in a narrower band, so hence the name narrowband IoT. And finally, you have also a development of legacy 2G technologies, 2G networks, especially aimed at areas where 2G technologies, 2G networks are still very prevalent. It's called EC GSM IoT, standing for Extended Coverage GSM IoT. What all of these 3 standardized technologies have in common is that they are based on the regular cellular standardized technologies. They are very compatible one with another, really, and you will see in the future that many operators will deploy not just one, but in fact will deploy 2 or maybe 3 of them. On the device side, as a user, you may see that many devices will also support several, if not all, of these technologies, so that as a user, you may not necessarily be at ask yourself the question of which one to choose, at least in the first step. So, on the one hand, standards-based technologies. On the other hand, proprietary. The standards-based technology, because of that standardization process, have taken a little bit more time to come onto the market, but networks and devices are available now. The big advantage of having standardized technologies, as we can see on this slide, is that because it is standardized, it's being made available by all stakeholders of the ecosystem, all suppliers, and so it's globally available in America, in Africa, Europe, Asia, Asia Pacific. So it's really available worldwide in terms of devices and also in terms of networks. It has a slighter edge in terms of security, because being based on the regular cellular network with security in mind, it has an advantage over security. The third advantage is that it is in the journey of an evolution of cellular networks from 2G to 3G to 4G to LPWA and then on to 5G. Very often the question is asked, well, why not wait for 5G? In fact, these networks, LTE-M and narrowband IoT, these technologies are already on the path to 5G and largely compliant with what will be needed for 5G. They do support mobile applications. Mobile, so the cellular network, the mobile networks have been built with the purpose of supporting mobile applications very well. You have an ensured quality of service. That's also very important. It has, to be honest, not much to do with the fact that it's being standardized. It has to do with the fact that these technologies are used in so-called licensed spectrum, where the radio wave, the spectrum, is dedicated to a given network operator, so that you don't get the interferences you could get with the non-standardized, with the proprietary technologies. And the last and sixth most obvious advantage of standardized 3GPP technology is that they also do support real-time application, bidirectional communication, so that you really can expect an always-on experience with your LPWA devices that you don't get with proprietary technologies, because they have not been built with that in mind. So these are the high-level advantages of these standards-based technology. But what was really needed, as I said earlier, in order to enable new applications, new use cases for the IoT, for LPWA, was to solve the challenge, to answer to the challenge of what we call the 4 C's of LPWA. So the 4 C's being, as you can see here, cost, coverage, current, and capacity. So meaning you need to have solutions that are more cost-effective than your legacy 4G solutions. It has to have a far better coverage, because very often lack of cellular coverage in some locations made it unrealistic to deploy all across the board an IoT solution that would work everywhere. It has to be much more effective in terms of current consumption, energy consumption, meaning that you can last with devices for more than 10 years on just batteries. So that's also very important, not being hooked to the power network. And finally, and that's also an aspect that's very present in 5G networks, because we expect those applications to explode in terms of numbers and volume, it has to be able, these technologies have to be able to support millions and millions of devices in the same cells, in the same geographical area, using the same amount of radio spectrum. So they need to be very efficient in terms of radio usage. So now, what I'm going to walk you through quickly, again, in that little time, we can't go into all the details, but at a high level, I will explain to you how we can answer that challenge of the 4 C's: cost, coverage, current, and capacity with these new cellular LPWA technologies. First of all, cost. Of course, the cost is very important. It doesn't solve anything, but the more cost-optimized the solution is, the better off the better off you are, and the more devices you can deploy. So think in terms of cost. What you get is about a 50% reduction in terms of cost. That brings cellular about at the level of a Wi-Fi or a Bluetooth solution, with all the advantages that I mentioned earlier of being standardized cellular, and in particular, not having to go through a Wi-Fi or a Bluetooth gateway, so being directly reachable. And at a high level, how this is done is basically by reducing, so two things, as you can see here. First, reducing the number of components in a chipset and in a module. So the technology is simpler because it is lower power, because there have been some compromises made on how the technology is complex. You need less components. And so that's the hardware. And also on the subscription side, of course, because you still need to pay cellular subscription, because on the network side as well, the technology is much more simpler. The network operators are expected and are already offering subscriptions at a much lower monthly or annual subscription rate. And in detail, how this is really done on the device side and also on the network side. So we are using a technology called half duplex. So it means that instead of having radio transmitters and transceivers being able to transceive and receive at the same time exactly, so they just they send, receive very quickly. So for the user, it doesn't really make a difference. But at the module design, at the chipset design, it helps a lot. Thanks to that as well, because we're using half duplex, we can save on filters, and we can also use what's called software-defined radio, meaning that now these devices can be compatible with just the software setting with all the different networks across the world, in North America, in Europe, in Japan, in China, where regular 4G devices always had to be compatible with the frequencies used in specific areas of the world. Now with these technologies, it's another gain that you can deploy them everywhere thanks to this half duplex and software-defined radio. They also have a single antenna, and of course, because they have the lower bandwidth, so a reduced speed, really, don't expect to be as fast as you would be with your regular 4G, say, Category 6 device. You're closer to your good old, I would say, GPRS speed. You can still do a lot of stuff with GPRS, and certainly much more than you can do with Sigfox or LoRa, but still, it's not full speed mobile broadband 4G. But because it's lower bandwidth and lower speed, then we can win on the number of components. So that's on the cost side. Now let's see on the next point, which is coverage, which is also a critical thing, because we needed really to get coverage so good that you wanted to be sure that you could have IoT devices in your basement that would still get coverage. This is measured in what's called decibels. So what we get in terms of coverage is a 20 decibel improvement compared to regular 4G technology. It's about a 5 to 10 times improvement in terms of range if you're looking at the free range on the countryside in terms of distance. In a urban environment, of course, it depends on how many walls and that kind of stuff, but it's much, much, much better. Because of that, you can now have in-building and underground coverage, like I said, in your basement. Of course, if you're going as a 6 stories down in a parking lot, you may still have difficulties, let's be honest. But now you have so much better that you can seriously think about deploying those solutions everywhere. And also extended coverage on the countryside means that you can reach very remote locations as well much more easily. And again, the way it is done technically, I won't really enter into the technical details, but you can look that up by yourself. You can ask questions if you really want to know, but there are 4 main ways to do that. First, you repeat the same frame, with a little bit of a difference, so that when the receiver gets just part of the signal, because it's been repeated by aggregating the bits of messages it got, well, in the end, it can reconstruct the original message. That's really how it is done. You can use, so this is called repetition and hybrid automatic repeat request. Frequency hopping is used, and other features such as power spectral density is also used, and selective scheduling. So quite a very specific radio details. But the bottom line is much, much better coverage, and that's one of the things that was really needed. Now, the next point, the next C, is about current, so power consumption. And again, cellular solutions were known to be very power hungry. Now, what we can achieve is about 75 times lower power consumption on these devices compared to regular cellular devices, which means that using batteries, and Dima will walk us through more details about this power savings, but you're very, very secure, and you can very realistically expect to last 10 years or more with batteries. Of course, it depends on how often you will transmit and how big your battery is, but that's kind of an order of magnitude. And the way to do that is really using by using power saving networks updates. There are strategies where the device can wake up faster and then go faster into sleep. And the current silicon design in sleep mode is much lower. And the names of these techniques that are used are power saving modes, so PSM, which is essentially the hibernation mode of your laptop that's exposed to IoT devices, EDRX, so extended discontinuous reception, and something that's called small data optimization. But using all of these techniques, bottom line is, again, you can last for more than 10 years on cellular devices, which is unprecedented. Now, moving faster to the last C, which is very important as well, but more for network operators, to be honest. As customers, you just expect the network to work. But thanks to the increase of network capacity and more efficient usage of the radio spectrum, LPWA devices can go toward one of these 5G requirements that they can support 1 million of devices, users, devices, per square kilometer. And we can do that with those technologies, again, using some technical optimizations in signaling, in narrowband transmission, and what you can see on the slide. So the 4 C's, again, so cost, of course, but also coverage, consumption, and capacity. That's what you get with those technologies. Now, I will wrap up with an overview, because I talked at the beginning about the 3 sub-technologies in the LPWA network. So I did mention EC, GSM, IoT, which is an evolution of 2G, but focusing on the 2 4G technologies, you've got narrowband IoT and LTE-M. So do you have to choose? Well, yes and no, not necessarily. At a high level, what you should keep in mind is that narrowband IoT has been much more optimized for very low data rates. So we're speaking about 60 kilobits per second, where LTE-M is a little bit higher, around 300 kilobits per second. So that's where you are. And narrowband IoT is very much focused on static applications. It doesn't support mobility that well, where LTE-M supports mobility just like any other cellular technology. So LTE-M has a better latency, so and also can support voice as well, so voice over IP, over LTE. So these are the main differences really between narrowband IoT and LTE-M. Now, that means that when you look at these 2 technologies, the main factors you will have to keep in mind, of course, is first, easily available by your network operator. So some operators like China Mobile, Vodafone, Deutsche Telekom have started to deploy narrowband IoT, and they're now working on the LTE-M. That will be available in the next couple of months. Other network operators like AT&T, Telstra, and Orange have done the other way around, while others still, like Telefonica, have just said, okay, we'll just do both at the same time. So you really want to look at which technology is supported by your operator, what the price is of your subscription, and how flexible it is, keeping in mind that both technologies are already ready for 5G anyway. And to talk about regional availability, so I will just show you a map of the coverage, worldwide of these technologies. So according to the GSM Association, so you can see the number of countries already. So mostly in North America, in the United States, so LTE-M is deployed now. So that's the light blue. In yellow, in Europe and in China, you've got a narrowband IoT. In Europe, you've got some LTE-M as well. And then in the dark blue, like Japan, Australia, like Thailand or Turkey, you've got both technologies. But keep in mind that this is today, and in, I would say, 18 months from now, you'll have all technologies everywhere. An important thing to keep in mind when you look at that map as well is also that the gray areas are not areas where you don't have coverage. You still have your regular cellular coverage. So don't forget that when you don't have the LPWA coverage, you still have your regular cellular coverage. Now, the predicted, I was speaking about that earlier, so in even just a couple of months, or in even like 6 months, this is how it will look like. Again, the gray areas are not no coverage areas. You still have 2G and regular 4G coverage in most of those areas anyway. So before I hand over to Dima, I have a very last slide. So with just a couple of things I would like you to keep in mind when you design your solution. So some considerations. We did talk about low power first, and of course, the strategy of how you transmit, how often, the design of your battery, and so on, and Dima will go a lot in detail about that, is one aspect. But there are other aspects to keep in mind as well. I did touch a little bit upon the ability of your module to fall back onto regular 2G. It's very important in some regions because, well, even regular 4G networks, I live in France, for example, and on the countryside, you don't have 4G networks. You just have the good old 2G network. So if you want a solution that's really usable everywhere, you probably should think about having a design that includes 2G fallback as well. Multimode support, we did talk a little bit about the differences between the LTE-M and narrowband IoT. A lot of devices do support both technologies, and that's certainly a good thing to keep in mind that maybe, well, you should strive to have that. One aspect also to keep in mind is a subscription, so the SIM card. Very often people ask, so what about the SIM card? Do we still need a SIM card? Yes, you do. But don't forget that these days you have technologies called embedded SIMs, or also EUICCs or eSIMs. There are a small component, it's a hardware component that, and you can deploy and be on a network operator like Sierra Wireless, for example, because we also offer connectivity services. But after a time, after 3-4 years, if you're not happy for whatever reason, if you want to change, using embedded SIMs, you can remotely reprogram your SIM. You don't have to go on site and switch the physical SIM. You can just reprogram it over the air and switch to, say, Orange, and then all of a sudden you're an Orange customer. And so this freedom is very important to keep in mind when you design your low-power application, IoT applications. Whether you need GNSS, so positioning, so GPS, Galileo, Baidu, so these technologies is certainly something to keep in mind. The availability of reference designs, so how easy it is to bootstrap and start up your project. And also one thing that we stress very much at Sierra Wireless is to have a scalable form factor for your cellular modules. So the cellular chips you will put inside your device, if you want to change the technology and at some point you go from 3G to 4G to broadband 4G, in some point in the future to 5G, do you need to redesign your whole device because the pins have changed location somewhere? It's very important. At Sierra Wireless, we have scalable modules with the exact same pin-to-pin compatible modules, regardless of the technology, and that's certainly something that's very important to keep in mind. Keep in mind that you must be able to upgrade. That's what's in the text on that slide. Be able to upgrade remotely. So not only the SIM I was talking about earlier, but be able to still do software, firmware upgrade, for example, because your solution will live over time. New features will be deployed in 3GPP release 14, and then eventually going to 5G networks. So keep in mind that what you deploy in the field must live probably more than 10 years if you're looking at more than 10 years of battery life. And with that consideration, talking about battery life, I will leave the floor to Dima. Dima, to you.
Hi. Thank you very much, Nicolas. It was a very interesting overview of the technology. And I'll deep dive a little bit more into what we can do on a power consumption of the chipset and the module itself. And I do want to start with highlighting that cellular devices or IoT devices are very much different from the smartphones. And that means that when you design a chip for LPWA or your IoT device, you should focus on totally different KPI compared to a smartphone. For example, all of us are using smartphones. We care about our battery time, but our use case is different. We upload files, we download files, we see YouTube videos, doing voice calls, and quite a lot of web browsing, and Facebook, some of us. LPWA devices are totally different. They're very lazy devices usually, mainly asleep, therefore standby power consumption is critical. And when they transmit data, it's mostly very small packets of data. And therefore device should be optimized, the device and the application should be optimized to send those short messages like location, temperature, sensor data, or actuation like open a door, close the door, things like that. And probably the last and still very important item is to talk about the photo energy. When we deploy a device that should stay in field for about 10 years, we should take care of the photo. And we also need to consider the photo energy when we deploy the devices, because we don't want to dry the battery after a few years if we are doing the firmware over-the-air upgrade to the device. And now I would like to touch a little bit about what does it mean to make a low-power device. And this is actually quite a long journey, because there are many, many components, and each one has a tremendous influence on the power consumption itself. And the first and probably the most essential parameter is to select the right module and the right chipset. If you start on the wrong foot, then anything else you do is very difficult. So please, when you check or choose your module or chipset vendor, or read the datasheet, take a look on the parameters I've just spoke about, like EDRX power consumption, energy to send data. This will show you, this would be your building stone to your application. The next, number 2, would be choose the optimal network. We see now many carriers say we have everything, but you need to actually deep dive and see, do they support NB, do they support Cat-M1, what is the quality of their coverage, and also what technologies are supported within the network. Do they support EDRX? Do they support PSM? What about release assistant indication, which is advanced release 14 feature? What is the quality of the coverage? All that can have a significant impact on your power consumption performance. And actually, we noticed that having dual mode devices like Cat-M1 NB1 can actually help the power consumption as well, because you can choose the right network according to your location and right technology according to the data patterns you are working with, saying that Cat-M1 usually have slightly better power consumption than NB. However, depending on the deployment, you do want to have both. The next one would be number 3, and I'll deep dive only into that bullet, is choosing the right network parameters, which is the PSM timers and EDRX timers, and we'll touch on the next slides. But before we're doing so, the additional parameters that impact your performance severely. One is, if you look at trace of what your IoT device is doing, then you'll notice that first thing after some timeout, it's going to look to find the IP address of the server, so you'll find a DNS request. And while they are meaningful on our PCs and smartphones, sometimes DNS requests can be almost the same power as the message we want to send after. Therefore, take a look on the timeouts of your DNS settings and where your servers are located. So if you work in US, it's better to work with US cloud hosted servers, and if you're in Europe, to do the same and not travel across the ocean from Europe to US just because you didn't thought that latency can impact your power consumption. The next parameter would be when we work with the cloud servers to check which protocol they use. And there is a big variety. Some people just use WebSockets, which are very simple. And we also see many IoT-based protocols coming from different vendors now. Some use MQTT, the other would use co-op. We'll find lightweight M2M protocols. And we also see some MQTT Ascend, which is low-cost MQTT protocol. So you should take this into your power consumption consideration when you're choosing the protocol and the web service. The next one would be your security scheme and certificates. It's interesting enough, but if you think of application which sends your temperature data every few hours, you only want to send a few bytes of data which represent the temperature and probably the ID of the device and the time. And again, if you trace accurately what's actually happening on the network level, you'll find that you often exchange the certificates. And therefore, you can find yourself in a situation where you only want to, say, send 5 bytes of data, and you ended up sending 5 kilobytes of data exchanging certificates. Therefore, you should take a look on which certificates you use, how often you exchange them, and what the timeouts are. And this brings me to number 7, which is the transport layer protocol. And here again, you can use TCP, and then your round-trip delay is important. UDP is slightly lighter protocol, less bytes to send. If it's really short message, maybe SMS is the right solution. You just send a message and go to sleep. All that is relevant, and you need to consider that. And the last and not least, when you're doing your application, think of power consumption. Every time you communicate with the server, that means you're wasting your energy in the device. So you have to think across all the layers, from the network to the device to the LTE to the cloud vendor selection to the protocol selection, and also the application design. You need to think about all those items, or when you design all those items, you have to think about power consumption. It's very important for your devices. And Nicola spoke a little bit about PSM in the EDRX. I want to touch it slightly and then jump into the slides that's actually showing you how to use them. But first, what is the difference between the two? PSM is, like Nicola said, is your hibernation mode. Device goes to sleep, and it's mostly suitable for devices with device-originated traffic, meaning that if I want periodically send some data like temperature or event-driven data like door was open, door was closed, this would be the best protocol because device is not wasting any energy on monitoring the paging signals from the network. And you can program your device to a very long timer. So basically, if I'm putting the sensor in some garage door somewhere, it can communicate with the network with a maximum period of 12 days. And that means it really saves most of the power for a standby mode and not wasting any power. So the maximum period between the data cycles or data transferred in the network, and we call it time area update, is 12 days. And you, of course, can make it shorter if relevant. Also important to note that data is device-driven, meaning device can go to sleep, and if you have the data to be sent to the network every 10 minutes, it can still do it. And this is the PSM. EDRX is a slightly different animal. In EDRX, device being registered for the network all the time, and therefore it can respond to network requests. However, you can increase the paging cycle or the latency that you allow to network to trigger the device, and by doing so, you consume power. For example, if I want to open a door from my smartphone, I cannot wait for 10 seconds for signal to come in. However, if I want to program a new irrigation program to my computer in my backyard, then of course I can wait 10 or 20 seconds to do that, and this will not impact my user experience while helping significantly to the power consumption of the device. So those are the two cornerstones of the low power saving techniques within the LTE. And the last thing to add about that, you can switch dynamically between the two. For example, in a tracker device, if your tracker is on the move, you want to be in EDRX mode and therefore reachable by the cloud service. And once device reaches its destination, it can send its location and go to sleep in the PSM mode. And by changing those two modes, you can achieve very attractive power consumption for various devices. And now I want to talk a little bit more how you select between the two, because this question is very often being asked by many of our customers. And when I look into this, or trying to find a way or criteria to select between the modes, there are two main inputs. One is the application latency, which we just spoke about. For example, smoke detector has no application latency from the cloud, meaning when device wants to transmit, it transmits, but cloud never trying to reach the device. And the other parameter could be the data exchange frequency. The more frequently we exchange the data, the less sensitive we are to our sleep mode, and therefore we can be more flexible with that. And the most basic or interesting examples for very clear PSM scenarios are devices like a smoke detector, an Amazon Dash button, some of the gas meters which not require communication from the cloud to the gas meter. Many water meters will also use PSM mode, which is not reachable, and you just have a reading once a day. Also, parking meters are pretty much the same. Every time you swap your credit card, you just want to say, update the cloud, something happened, but cloud never needs to reach the parking meter itself. However, it's also possible to have the PSM mode on devices where cloud service do want to communicate with the device. For one example could be pallets or containers, and the other example would be the irrigation valve I just spoke about. A device can send data every few hours, and but also cloud can configure the device. For example, if this is a pallet, it can wake up, send the data, okay, I reached the warehouse, and then cloud can configure the device. Well, if this is the case, please go to sleep for next 10 hours. I don't need any updates. Therefore, even if cloud need to reach the device, in some cases you still can work with the PSM mode. And for the EDRX, there is another set of applications, and some of them are very clear while other is there. In this case, it's less clear, but one of the examples, and we see it quite often, is a gas meter with remote shutdown functionality. If you want to have a device, still same metering device, but you want to be able to shut down it remotely, it's a clear case where you need to work with the EDRX mode. Another example would be a smart band or tracker, where you do want to send messages or find my kid now, find my tracker, then you really have to be in EDRX mode. And the shorter the application latency you can allow, the shorter the period is. For example, an example of a smart bike, I want to approach the bike and I want it to be open immediately, and therefore the period should be seconds and not minutes as before. And of course, it will cost some power. And now I'd like to give you an example of, if you use those techniques correctly, what are the power consumption and what are the scenarios we can, or what are the battery life that we can actually achieve with our devices. The first example would be the smart band from the previous slide. If I'm only sending 1 kilobyte of data every 15 minutes, still being in EDRX mode, the power consumption of the device or the battery could last for up to 100 days in that scenario. And this is small battery, and this is very attractive for the smart bands. The other example could be Amazon Dash button, where we can have up to 10K click over 3 years on a single AAA battery. The next example is I'm jumping into more of industrial application, where we have a metering application that can, on a single battery, to last for 7 years, 2 batteries for 15. And as it's going on, we are getting to the application where, for example, for a smoke detector or a water meter, one battery can last for up to 15 years, which is a really cool use case now. In those days, using previous technology, we hear our customers that had to use $10 or $20 batteries for 10 years of operation, and now we talk about sub-dollar battery that can last for 15 years, and this is a substantial difference of a new technology.
So that will take us into the home stretch, and we, at this point, will hand it off to, I believe, Remy Marturtino to take us into the Q&A. Remy, welcome.
Thank you. Great to hear the story from Nicolas and Dima on the networks technology improvement. That's GSMA is coming up, and so the implementation at device level. I'd like to touch on another side of the stories that can affect also the power budget for application is how our customers, device makers, service provider alike are managing the data. There is to be some efficiency in the way we manage the data to maximize the network and the edge device capabilities to lower the power consumption of the solution. So let's look at an analogy. I use the smart home analogy here. We can see it's a big market, of course, in the IoT space. A lot of new product coming to the market that are the foundation for home automation, saving power, like smart thermostat or smart light bulbs and smart appliance. By buying those products, we have the foundation for a smarter home, but if we are still using quite a bit of electricity, cranking the light on all day long, that would defeat the purpose of those equipment, and so we still consume a lot of energy. This is a parallel to be done with LPWAN technology. Those are the foundation, but we need to be smart on how to use them, and the key is data, because the way we send data to the cloud and how we manage it will affect our application. So if I see the slides here, how do we translate that at the end-to-end system level? There are two major considerations to take into account, and that are pretty standard when we develop an IoT LP1 application. The first thing to recognize is that a lot of the LP1 devices out there would be generating a lot of data, but not all the data is relevant and that needs to be sent, and they definitely not right away. So we need to send rules to the device in a smart way, a very lightweight way, on how it needs to manage the data, prioritize it, and filter it. And we call this capability at the edge stream processing, as to processing the data at the edge before sending it to the cloud. Another thing is that those rules will evolve over time. During the development phase, for example, we might want to change certain behavior of the device. The networks themselves might evolve as well, or we are going to learn a bit also on the application, and thus we want to adapt our application at the edge the same way our smart thermostat recognize our patterns. So we need a centralized way to adjust these rules at the edge and optimize them. It needs to be lightweight for that, and we don't want to always have to change the code, recompile that firmware and that code, and do FOTA every time to make an adjustment to the behavior of the edge device. So we want to be able to tweak those rules, this capability. We will have to we call that capability data orchestration. Both those capabilities, so stream processing and data orchestration, need to work in sync to make the most of this underlying LP1 network technologies. So now let's illustrate that with an example. But first, I would just want to make sure the audience understand what we mean by edge device. There's a lot of things in the market talking about edge. What we mean here is our targeted are deep edge devices. That means that they are usually constrained, are not powered, can rely on battery for the most part, and will run on a small CPU as to save battery life. Usually when we hear about edge devices are less constrained, it can be a gateway or router, for example. In this example, we will connect, for example, packages to track them instead of the entire truck, or for example, in the agriculture market, we are monitoring the IoT soil monitoring sensor instead of the gateway that will aggregate thousands of sensors deployed in the field. So that's the differentiation that we are making when we do this discussion about edge and edge monitoring. So on that example, let's take the medical service and lab transport industry. a lot of those companies came to us with very interesting use cases. For example, they want to manage lab specimens that are being transported from one hospital to the other in some totes, and they need to maintain a certain temperature to ensure the integrity of the specimen, like a blood test or vaccine. Regulation also requires proof that specimen temperature stayed within a certain range. And they require a timestamp and a location information. So where we can leverage the stream processing and data orchestration. So on the stream processing side, we are going to measure the temperature on a regular basis, but we don't need to send that every minute. We collect the information, so we can buffer it and then send it at a special time, like once a day or once every few hours. Same way for location information, we can put geofencing around a certain location and hospital of those mentioned by those companies, and then just send an alert when we cross those locations. So that's how we can leverage the stream processing. On the data orchestration side, depending on the specimen type or location information, we might want to tweak the threshold at the edge or the frequency of the reporting and reading, and we don't want to send a full firmware over the air upgrade to do that and new coding, etc. So we need to find a way to just send a snippet of code, some rules engine at the edge, very lightweight to change those behavior of the device. Similarly, we can add a new feature like a tamper alert. So a customer wanted to have light sensors on the tot and be alerted when it's open, and we can push those rules to the edge very easily and flexibly by those data orchestration techniques. So that's some consideration again to optimize the power budget of your overall application. And then the last slide was just a few other consideration. For sure, you need a lightweight way to manage, to measure the battery power at the edge. We have technology that can allow that. We touched on the security, but there needs to be a lightweight protocol to handle handshake between the device and the cloud. And so you need to leverage the latest protocol to do so. So you limit the overhead. And then on the location side, of course, you are thinking about GNSS a lot for outdoor tracking application, but we see that Cell ID and Wi-Fi can be good complement to reach a trade-off in terms of power consumption and give you still some good location services information. So that's also some consideration here for lowering your power optimization.
Great. Thanks for that, Remy. And that'll take us into the Q&A portion of the event. For those of you who haven't submitted questions but have them, please submit them, and we'll get to as many of them as we can. So, Nicholas, it's been a while since we've spoken to you. So, question here, how long will NB-IoT and CAT-M last? They're new, but is there a roadmap out there for replacing solutions?
Well, of course, there's 5G. I'll be quite short but clear on that. LTE-M and Narrowband IoT are designed into 5G so that 5G core networks can still work with the radio technologies LTE-M and Narrowband IoT. So it will last for at least 10 or 20 years, which is normal considering that when you deploy, you aim at having a battery life of 10 more years. So it will last for probably 1 or 2 decades at least.
Excellent. All right, moving right along now to Dima. If you were to report, say, once a day, which technology of the ones that you covered previously, DRX, eDRX, et cetera, would be the most battery efficient while also offering the longest range?
That's a great question. I think most likely I would say TSM. You can reach really few microamps of average power consumption for that. But we need to deep dive into that scenario. If you ever need to trigger the device from the cloud, that could reverse my question.
Excellent.
Or my answer.
All right. Now, short break for you, Remy, but no rest for the weary. How small can these devices be in practice? Not just for the chip, but for the module and the finished device itself?
Yeah, I mean, if people look at some of our roadmap products that are on our website, I mean, we reached some good size like 15 by 18 millimeter, and that's just the beginning of the integration capabilities that we are going to enable moving forward. So we used to do 22 by 23, reaching now 15 by 18, and then it will be lower as we go forward in time. So yeah, simplification of the system really is this is what the LPWAN is about, is size reduction, cost reduction, and then power.
Excellent. Nicholas, back to you, and this is a great question. Do you have any information on real-world subscription costs for GSM operators using NB-IoT and or Cat-M1?
Very good question indeed. So, of course, it will depend on your network operator, but not avoiding the question completely. The order of magnitude, and if you look at the market, you're talking about a couple of dollars a year for each device. So that's really where you're at, $1, $2, $3 a year for a device. That's where you are, depending on which service, which coverage, and so on. But that's where you are.
Wow. Okay. Let's see. Another one for you, Remy. For future LTE-M and NB-IoT devices, will Sierra allow onboard analytics processing in addition to RF processing?
Yeah, I think that's the strategy to enable cost reduction, more integration. So we need to enable processing and an application, a lightweight application. I talk about this stream processing, so really enabling some analytics at the edge. Simple. We are not doing deep learning here, but a lot of the IoT application can really leverage what we are doing at the device level instead of sending all the data to the cloud and doing this analytics in the cloud. So we can do a lot of pre-processing at the edge and enable the IoT space as such.
Excellent. So there's sort of a two-parter here for you, Nicholas, and I'll try and wrap this up in a way that's digestible. What are your suggestions regarding fallback if no Cat-M or NB-IoT network is available? And then secondly, what happens to legacy systems when 5G is introduced?
Okay, so that's a two-part question. So first, I did mention that 2G networks in some geographies are going to be around for some time. So if you don't have a 4G coverage, either LTE-M or narrowband IoT, I will strongly recommend you to look for falling back onto regular 2G. Now, speaking of the compatibility with 5G, it's really a matter of, like I said, the 5G networks, the core networks have been designed so that they can integrate LTE-M and narrowband IoT. So nothing will happen to your solutions when 5G is introduced. It will just continue to run, like I said, for at least 1 or 2 decades. So no problem at all there.
Excellent. All right. Let's see. Filter through here. Remy, can a software update to the end node cause an increase in latency with stream processing data updates?
So actually, that's the relevance of the stream processing is instead of doing a full FOTA, and takes quite a bit of space and latency from the cloud to the device. Here we are looking at a very small snippet of code, potentially a JavaScript, algorithm. So that's very lightweight, and usually should not even increase the latency between the cloud and the device. And so that's why we like this stream processing capabilities instead of doing a full-fledged firmware over the air. You can change the behavior of the device at the edge by sending just a rules engine and JavaScript, for example. So.
Thank you, gentlemen. And that brings us to the end of today's presentation. Experts from Altair Semiconductor and Sierra Wireless will be in touch with each of you who submitted questions throughout the discussion. And if you'll be attending European Utility Week in Vienna next week, Sierra Wireless welcomes you to their stand, AB50, to continue this discussion in person. From the team at Smart Energy International, we thank you for your participation, and be sure to keep abreast of upcoming webinars on smart-energy.com.